Hello and welcome back to the Security Conversations podcast. My guest is Dr. Sergey Bratus, Program Manager at DARPA and an Associate Professor at Dartmouth College. Welcome to the show, Dr. Bratus. How are you?
Doing well. It's great to be here. Just Sergey.
Hi, Sergey. Let's start at DARPA. What does a Program Manager at DARPA do and what are your priorities there?
As a program manager, I create the calls and formulate the problems that we want to solve for the long perspective. You may have heard that DARPA seeks to prevent strategic surprise and create strategic surprise. What that means is that with our current reliance on technology, we don't want to see some basic elements of our computing infrastructure suddenly revealed as vulnerable and then having to scramble to somehow deal with that vulnerability. So most of my interests in my position as a program manager have been what are the fundamental scientific problems that we need to solve to secure our computing infrastructure.
One of the things about DARPA is by design, these program managers' tenures are time boxed, 2 years to 4 years. This is your second run there at DARPA. Why did you decide to come back? Is this something that truly excites you? And what is the big picture promise?
It absolutely does excite me, and I'm trying to give it my absolute best. What we'd like to see today, 10 years from now, 20 years from now, is computers we could finally trust. And this is probably the most exciting thing of all for somebody who's been looking at the mathematical implications of exploitability, the empirical science of how computers that we build are not exactly what we wanted to build, but other things, including exploitable and robustly exploitable things. This is my hope of helping that science to advance.
Is that even something that's realistic? Computers that do exactly what we want it to do? I mean, the idea of hacking and the idea of compromising is to just get this machine to do something that it was not meant to do. How realistic should we be in our mindsets around what security actually is?
That's right. That is precisely so. And even posing the right problem for the computer scientists, for the mathematicians to solve, must take this into account. From the hacker citizen science, and speaking as an attendee at DEF CON since the Alexis Park days, one thing that we know empirically about computers is that whenever we build a system, whenever we build a system of systems, it has this really long shadow of emergent behaviors, unintended behaviors that are not just incidental. Otherwise, they wouldn't be continually, reusably, and portably exploitable. So what does that mean for the foundations of computer science? Can there be a mathematical characterization of how these emergent behaviors emerge? Where do they come from? We have models such as the Turing machine or the lambda calculus or finite automata or push-down automata to get more into the nitty-gritty. Where do our real systems diverge from those models? And why is this divergence ubiquitous? I think, personally, that these are the most interesting questions of the age that the hacker community has been posing for the theory community. If you think back to Church and Turing and von Neumann and Hilbert, they would be excited about those problems because the nature of science is explaining the empirical phenomena. How do we explain exploitability? And then, of course, from that question, we would have the answer on how to reduce it.
Is there a massive difference between the theory community and the people putting security into practice? And I ask the question this way. Like, we have a general understanding of what good security hygiene looks like, about what security development processes look like. We're well into shift left and moving everything left. And we still have a cybersecurity nightmare on our hands. Is theory so much different from the practical that it's just...
No, let me question that. Do we have a really good understanding of cyber hygiene? So let me talk about one of my programs, Safe Documents or Safe Docs, which is really about how do we build parsers that we can trust? How do we build parsers and input validators that would actually validate input rather than being exploitable and the hacker's best friend reacting to crafted input? Do we understand the security hygiene or security best practices for creating a parser or designing a data format? In fact, the reality seems to be that an implementation is doomed at the point when the data format is designed and some features in it are too ambiguous or too powerful. There is a scientific direction here, which I helped to get off the ground, called language theoretic security, that characterizes weaknesses in protocol and format designs that then doom implementations to being vulnerable. So there is theory, and then there is practice. In practice, we've converged to never roll your own crypto. You are going to make a mistake. Your users are going to be vulnerable. Right. What about never roll your own parser? We haven't quite converged to this. And if you look, the input validation or langsec bugs, they just continue. They're peaking. Each year I'm going to say, okay, this is the year of the peak langsec. The clouds are vulnerable. The electronic signature formats are vulnerable, and then the next year brings more and more surprises. So I would contend that we have not yet translated the proper science to the accessible hygiene for developers and designers of systems or even of data formats. SafeDocs, the program, aimed to do just that.
Fascinating project. I was watching a talk you did at Microsoft Research around this, and the idea that this goes all the way up back to the ISO formats. That this notion that a lot of the descriptions are not machine readable. You mentioned they're unambiguous. There's just these standards are hundreds and hundreds of pages with these ambiguities everywhere. Now we're trying to get machines to clean up that ambiguity, and you guys have already contributed a lot to getting those format fixed. That's tech debt. That's why, is it even tractable, that kind of debt that we're absorbing from the formats? And like you're mentioning, these new formats are coming on stream every day. Are we just creating more code than we can ever realistically try to secure?
We might be, and this is why we need to rethink our approaches to information interchange. So as you said, if you want to implement a format, let's take PDF, because we looked at PDF, that's over 1,000 pages for just the core format specification. Now, what is the chance that two reasonable developers, two reasonable humans, are going to read all those pages and come up with exactly the same interpretation of what they say?
But we don't want to get there, right? We want it to be machine readable, right?
That's correct. That is the way forward. So not only do we want these formats to be codified in a machine-readable, human-intelligible form, we also want our parsers to be generated from those descriptions so that for two recipients of the same document or message, if we're talking about messaging formats, or streams, we can assert that we have proof that they are understood, parsed, and understood exactly the same way. Now, this is important for documents. This is important for protocols. This is important for authentication. Remember the X509 vulnerabilities when a certificate authority would see a request for certificate signing differently than the ultimate client, the browser, would see the same data in the signed certificate. You might think you just signed something for a low-value domain, but in fact, the client would be led to believe that you signed a statement about a high-value domain, Google or Facebook or any one of those. These are real. And the interesting thing is that these don't go away. Just recently, we had the psychic paper vulnerability, a year ago. And it was that kind of parser divergence, or as we say, parser differential. And it was a very impactful one. And they keep coming back because we hand roll our parsers. When we specify our formats, we fall back to natural language with its ambiguities and the normal human forgetfulness. Have I checked this property? Where am I in my parser code? Which properties have I checked? Which property am I actually checking? Which properties are yet to be checked? And of course, if you act on something that you haven't checked, there you go. It's your vulnerability. Most of the time, it's a memory corruption. It does not need to be memory corruption. It could be a request smuggling, which the clouds are now massively vulnerable to. You just look at the 2020 presentations along the lines of HTTP2, the sequel is always worse. That was not the work we funded, but it's a harbinger for things to come. The clouds are full of parser differentials.
Right.
The multiple middle boxes that the request traverses are full of parser differentials. With SafeDocs, there are finally tools, data definition languages, secure parser construction kits that allow one to create a parser one can trust and one can prove validates correctly a given set of conditions.
You have multiple participants in SafeDocs taking different approaches to this, right? Including folks at Microsoft and some other folks. What are the biggest promises from what is emerging out of SafeDocs?
Mm-hmm. So I have to make a small correction. Microsoft is not a performer. They were interested, and their Project Everest pursued the same line of scientific inquiry that you might call
so they're doing it
independently.
They're doing it independently.
SafeDocs,
right?
Perhaps looking at our publications, I don't know. They have in their paper cited prior language theoretic security research, which is great. You know, we feel that we've been heard. But the performers of SafeDocs have a really interesting structure. So you say that, are we listening to the scientists or are we listening to the hackers? Now, in SafeDocs, most performer teams include both theoreticians and familiar hacker companies, cybersecurity companies, whom you see presenting at DEF CON, Black Hat, and other security conferences, industry security conferences, citizen science security conferences. So SafeDocs is, in a way, a poster child for what DARPA does. It bridges communities. It brings together performers with different capabilities, somebody with a mathematical understanding, such as SRI, who have been doing formal verification, formal methods, for over 20 years since the dawn of formal methods, or longer than that. And on the other hand, you have hacker researchers who have been exploring those parser differentials, exploring parser vulnerabilities, and now they're working together on parsers that could be shown to be provably secure, or parsers that could be shown to be formally correct.
Are there any success stories you can tell about what SafeDocs have already done to improve the formats? What SafeDocs have already done to remove attack surfaces in certain places? Is there like some documented?
Certainly. Our biggest success story is our interaction with the PDF Association, which is the industry umbrella organization for anyone who uses PDF, and think Adobe, Microsoft, and others, but also think companies that make hardware interpreters for PDF, for high-speed printers that print much faster than the software could parse that. What we've done is we've created on SafeDocs, with the help of a PDF association, a model, a document object model for PDF, which is a machine-readable definition of all the objects that the PDF standard describes. And it is machine-readable, vendor-neutral, and you could check your own parsers or your own validators' idea of correctness against that model, removing the space in which those kinds of parser differentials or vulnerabilities due to them could hide. We also filed over 100 disambiguating edits to the PDF 2.0 standard maintained by the ISO, the International Organization for Standardization, and they have accepted most of them. So you see, this is where I, as a mathematician, as an academic, see the value of formal methods. The value of formal method is that you get a mathematical proof, but your proof may be irrelevant to practice. It may be expressing things that the practitioners already know. The true test of formal methods is that they can continually surprise the experts. The experts who have spent 20 years or more in their format, in designing their format. If we can show them that these are the corner cases that you have overlooked, that you have missed, that require more attention, then I feel we're succeeding in connecting the mathematics with the practice.
Why aren't we doing more of this? This marriage of academia, the two worlds, is something you've mastered. Why aren't we doing more of this? Why isn't this more of a whole of society approach to getting these formats fixed or to getting, work on parsers done?
So I would say that this is exactly what DARPA does. This is exactly what I see DARPA doing on my watch. And arguably, DARPA has been a leader in this for the society. This is how we progress. And then, of course, as a DARPA program shows that something is possible, we hope that the industry and the rest of society, through the experts interacting with those technologies, through the consortia of consumers of those technologies, will take them and carry it further. As at DARPA, we plant the seed. We show that this is possible. But I can give you another example. On my other program, Assured Micropatching, we're bringing together the verification and assurance, program analysis, and other key research topics that have been very important for academia with the practical art and science of patching a vulnerable application to which you don't necessarily have the source code or the build chain. And so we seek to reinvent decompilation. We seek to reinvent recompilation. We seek to create new classes of tools that give you the agility and the transparency to fix a binary, even though you might not have the vendor who originally wrote this code. They might already be extinct. They might have been out of business. They might be unavailable. And yet, we can take formal reasoning, mathematical reasoning about programs, and apply it at a point of vulnerability in the binary, extending the life of those devices, protecting their users. That's another example where we're bringing the hacker practice, the reverse engineer practice, the reverse engineer who's been called upon to understand the vulnerability and fix it somehow with the mainstream computer science.
And that's a critical project, because what you just described is stuff that's deployed in all deployments in critical places that, in many cases, we have kind of absorbed that risk as that will never be patched. You're saying mathematically and scientifically, we need to get to a place where we can patch those. Can you talk a little bit about some of the success of that?
Yeah, so the Assured Micropatching program, or AMP, is now in a more mature phase. We already have tools that make patching a binary an exercise in interpreting it, lifting it, and then having formulated and situated a patch. That in itself is a huge problem, right? So you know that a vulnerable version of OpenSSL or some other standard library isn't there, isn't this binary image. But once you get this image off of the device, it's just a stream of bits. Where is that library? Can we identify it? Can we match it up against the code which we think is there? These were all the problems that we posed on AMP and that we see performers solving. We see, for example, Ghidra plugins that answer to this, Anger, the open source symbolic execution and program analysis system, answering this, and a binary ninja, now including that kind of functionality that can match up code that you think is there with what's in the binary. So now that you've situated where you want the patch, of course, the answer could be the answer in the situation when you can recompile, right? Would be, oh, just go ahead and recompile. And that never works. Because if you use a slightly different version of the compiler, you never know what sort of binary code you're going to get. A small change to the code is not at all guaranteed to be a small change in the binary.
Right.
So what you need is a new class of a tool, which we call an assured recompiler. It's a sort of a compiler that cares about the currently existing binary image, does not discard it, learns from it, and seeks to disrupt it the least to affect the pointwise fix. And a lot of binaries are working because we tested them and we know they passed the tests, not because we have any stronger correctness guarantee. And so when you recompile that binary, again, pre-AMP, you would have to retest it the same way you tested the original.
Right.
With AMP, you can have an assurance argument that you understand, you've enumerated all of the new behaviors caused by this small binary patch, and you've minimized them. You're excluding the vulnerability and the associated behaviors, but you're disrupting nothing else. So that way, you can reduce your testing and you can roll out your patch faster. Again, as a DARPA fundamental research or applied research program, we can show feasibility. We can open source the tools and hope that the industry will start accepting that. And 10 years from now, a patch Tuesday of downloading gigabytes to patch a security vulnerability would be firmly in the past.
You think 10 years is a realistic window to get to a point where this is practical?
I would hope so. And that's certainly the horizon at which we're aiming. It takes a while for the industry to pick up scientific advances. When they're wrapped in tools and available for download,
right.
That
it's already in Ghidra, it's already in Binary Ninja. It's going to stay.
Yeah,
uptake
and
becomes a lot easier.
That's right. So it's been a huge boon for us that Ghidra has been open sourced. Even as a teacher, I can say it's great to be able to tell the students, download Ghidra. Prior to that, what could I say? Go buy yourselves
Go buy something very expensive.
Yeah, a student would not be.
It's really democratized. Ghidra has really democratized reverse engineering in many ways. I mean, the open sourcing of Ghidra has been a game changer, you would say, especially as with students coming into it, right?
That's right. Also, I really strongly believe in the leading role of the citizen science in information security.
Define that for me. Define citizen science.
Well, of course, you have academic science, credentialed institutions producing people with degrees, credentialed journals or conferences, publication venues that have peer review. It's an interesting fact of life that in computing, the discoveries of unintended behaviors, of emergent properties of computers have happened by and large outside of the credentialed institutions, outside of the credentialed peer-reviewed journals. You take a conference like DEF CON. If you wanted to understand how systems work, including how Unix worked on the binary level, what were the internals? What were the internals of dynamic libraries? What were the internals of the binary executable formats? You would go to DEF CON, or you would read FRAC. And FRAC would be as useful for you as any academic venue or more, because they would include proofs of concept that you could run.
You mentioned FRAC, POC, GTFO. There are some other examples of what you're describing here. I feel like a lot of that is driven by voluntary work. A lot of that is driven by just intellectual curiosity. Is there a place for that to be properly funded so that it's not as dependent entirely on people's spare time? You know, why isn't there a FRAC for every sector? Like, that's what I'm asking.
Yeah. Well, first of all, it's a labor of love, right? And it will remain a labor of love. As scientific research generally is or was. And DARPA has
There's a
done.
purity to that, right?
Yeah. But you see, DARPA has supported this research. The Cyber Fast Track program
Right,
run
the Mudge
by
program, right?
Mudge when he was a DARPA program manager was a prime example of that. And DARPA tries to work with non-traditional performers. I would direct your attention to the AICC challenge just announced at DEF CON, and I hope there will be more hackathon-style challenges. But ultimately, it's a labor of love, and the best we can do is to make sure that the academic science, the credentialed science, sees that for what it is, doesn't snub it, and is open to understanding and formalizing that enormous amount of empirical knowledge that exists in this community. And luckily, to an extent, this has been happening. You can now see FRAC being cited in scientific papers. You can now see DEF CON and Black Hat and other industry conference talks being cited in scientific papers. But it's a bridge building exercise, and I would not say that the bridge is complete and perfect.
Right, and there's always that friction too, right? There's always the friction between the purists and the academics and the hackers and the researchers and the vendors who are responsible for keeping this safe and who have, financial obligations and business priorities that are sometimes different from security priorities. And that friction is why it needs to be independent and why it needs to be pure, right?
That is true. And also, this is why we need to continue creating that space in which this interaction happens. For me, as a program manager, it's asking the right questions. It's posing the right problems and then creating a program that could support this research and bring these people together. For others, it could be creating challenges that the DEF CON attendees might resonate to. For others, it might be creating a space in the open source that these different communities can interact in. But long story short, the path to computers that we could finally trust certainly has that step in which academics and the hacker community are working more closely and are more attentive to each other.
You and I have been around this place long enough to see these hype cycles go crazy up and down with what the promise of blockchain, the promise of this, the promise of that. The latest is AI. You mentioned the AI Cyber Challenge out of DARPA, which is this 20 million program over a couple of years to try to get folks to really focus in on what generative AI is and how we can have it solve security problems. When you take into account all the hype up and down cycles that we've seen, are you bullish on AI? Are you there that this is the answer to society's main problems?
Well, when one is asked as a scientist, is X the answer to society's problems? One is bound to be skeptical because a scientist is bound to be skeptical. And of course, I can't speak for AICC because this is the creation of Perry Adams, a brilliant program manager who just joined our office. But this I would say, in AI, historically, having the right representation of knowledge or input or the space in which this kind of numerical magic happens has been historically a winning move. So I would say that AI, and this is my personal opinion, does not somehow invalidate symbolic approaches or mathematical approaches. What is likely to happen is that we will see a fusion of how we represent programs, how we reason about programs today, the symbolic approaches, and the neural machinery to see this kind of a neurosymbolic fusion. Because your typical translator model, your typical model that takes a large window of tokens and uses it as context, it doesn't necessarily have the understanding or any understanding of what these tokens mean. It might represent context, but it doesn't have the semantics. As we all know, in exploits, getting at the semantics And finding this additional emergent semantics that somehow got built into the system unwittingly is the trick. This is the weird machines theory of exploitation that I helped to start off. So I think we're going to go through phases when computing is presented differently, maybe in towers of representations from the binary to the source and to the desired objects, domain-specific objects, because ultimately you don't care about your C code or your Java code. You care about packets or images or messages. And so you should really be writing domain-specific languages when you can and using domain models. And that will get learned by neural mechanisms. And I think this is where the next amazing set of applications would come from. I don't think it would come from strictly neural approaches, but that's just my personal bet. I may be proven.
So there's always going to be this hybrid. Always going to be this hybrid need for semantics and for a human final touch. Is there?
Yes, or human annotation. I mean, even so, even today, when aligning models, people use humans, right? When tuning models, you have to ultimately understand if this is helpful to the humans or not, right? So I think that as builders of tools that connect binary and the intent, the executable code and the objects, that we're not going to be obsoleted by AI. If anything, we might be complemented by AI. But again, I have another program called vSpells. Recently, one of the performers was profiled in the register, which was interesting. And the idea there is that when you already have a large legacy system, you can interpret the code, source or binary, you can lift it, and then you can make improvements to the system or changes to the system at that higher level. God forbid you need to write C to change a C system. That is likely to lead to crashes. The more scale you have, the more likely you are to produce a crash in your production server. So we already see communities such as Linux community going on to a different way of changing the internals of the Linux kernel. But I think that approach will flourish more, and we hope to facilitate and accelerate it. And this is vSpells, the verified enhancements, verified security and performance enhancements for large legacy systems.
We just want to circle back to the AI thing for a little bit because we're starting to see some use cases emerging where Google is, for instance, using some generative AI technology, LLM technology, to expand code coverage of OSS fuzz, their open source fuzzing infrastructure. We've seen GitHub push, a lot of Copilot, like developer assistance type capabilities further left towards the developers. When I look at like your SafeDocs program and all these programs, is there room there where people can sprinkle AI magic dust and scale improvements? Is there room there? Like where should researchers be focused on when they're thinking about generative AI and security use cases?
So I will say definitely. And in fact, some of the researchers on SafeDocs are already applying that and are already looking at a more interesting problem of how far can AI help? If you consider the hierarchy of computing power, where is your current neural and your future neural-based AI on that scale? But once again, the question is semantics. We're describing a format. We're describing the properties, the structure, the relationships between the objects that the parser must enforce, right? Addressing this problem only on the level of, is this C code vulnerable? Why are you writing your parser in C, right? Is probably, well, because it's fast, right? Or because C has been around forever, or because it's easier to find C programmers. But the most important thing is connecting the unambiguous definition of the format with the code. And you can certainly use AI techniques for the program analysis task of show me that this parser actually enforces these properties. But as always, you can't defend what you can't define. So you need to define it first. And the better you define it, the less domain specific language, the less data definition language you have to write, the easier it is for the AI to learn and to potentially apply it to verifying your parser. This is something that our office has been interested in, certainly. Can AI help write verified code? You could look at the Provers program of the PM Brad Martin and other efforts that are associated with that. But long story short, you can't really defend what you can't define. And defining things unambiguously has been the best tool that security has. And I don't think it's going to change.
We're running out of time, so I have one last question to close on. Is this big drive around security by design and secure programs should be built software, everything should be built secure by design. I feel like there's so much ambiguity there to what that means. Each vendor defines that differently. Is that even a realistic expectation, this security by design? And where are your thoughts on the potential for this project?
So the key word is design, right? Design in this particular case means establishing the properties that the final software must have. In order to trust software, you have to specify what is it that you're trusting. For example, will it ever corrupt memory when being presented with an arbitrary or malicious input? And the answer to this has been safe programming languages. Safe programming languages would help eliminate a lot of the vulnerabilities, not all of them, because if you look at the string rewriting that has been plaguing clouds, again, this HTTP2, the sequel is always worse, is a prime example of that. Everything there that created those vulnerabilities is written in memory safe languages. Java, Python. Once you pin down what it means to have the secure design, it becomes a well-posed problem for the engineers, for the researchers, and for the hackers who would find counterexamples. An exploit is a proof by construction that a desired property does not hold. This, by the way, has been underemphasized for as long as I can remember. People think of proofs of exploits as these ad hoc, clever inventions, but in fact, the other thing that they are is constructive proofs that a property does not hold. For every exploit, there is a theorem. Long story short, it is definitely doable so long as we keep refining what it means to have a trustworthy software and how does that translate to the design, right? And in as much as I can, I will support those efforts in my remaining time as a PM. But that is certainly a fundamental research problem, the way I see it, because coming back to the very foundations of computer science, David Gilbert posed the Entscheidungsproblem. Can a computer decide if a mathematical statement is true? This is a question of, can a computer give me the answer to this kind of a problem? Can computers do this? What can't they do? What can they do? And how far we could trust them knowing that. So I would bring that kind of line of thinking in computer science that is exemplified by the citizen science of hacking, of exploitation, of vulnerability research, back to the very roots of understanding what computers are. And pretty much all of my programs tried to elicit that fact and bring it to the attention of both the hackers and the researchers.
All right, we'll leave it right there. Thank you very much, Sergey. Appreciated that. This has been a thrill for me. I've been a big fan of your work, read your books, looked at many of your talks over the years. So this has been a big thrill for me to talk to you. And I appreciate your time to come and spell out some of these answers for us. Thank you very much.
Thank you. And I'm a big fan of yours. So it's great to be here. It's a privilege. This might create some more questions from your audience. I'll be happy to engage. Thank you.